So if you're being asked to test for the presence of carbon and hydrogen, now one thing is this, to explain the test or to define the test. Now the compound is actually mixed with copper 2 oxide. All right, the compound is mixed with copper 2 oxide. Copper 2 oxide. Now the mixture is heated and vapor is evolved. So this mixing with copper 2 oxide first. Then secondly, the mixture is heated. So heated and vapor is evolved. All right. So now if the vapor turns to anhydrous copper 2 tetraoxosulfate 6 blue, the compound contains hydrogen. All right. So when it is heated and vapor is evolved, if that particular vapor turns to this anhydrous, this that is blue of this anhydrous copper 2 tetraoxosulfate 6, then it means that it contains hydrogen. Now, while if the vapor turns to lime water, you know what lime water is now? Lime water is calcium hydroxide. If it turns to lime water, okay, milky, if it turns to a milky form, then it means that the compound contains carbon. All right. So now, for instance, now if you want to write the reaction, for this, all right, the reaction for copper 2, okay. For instance, now if we have copper tetraoxosulfate, that is copper 2 tetraoxosulfate 6, which is CuSO4, all right, plus 5H2O. Now it will give you this anhydrous copper 2 tetraoxosulfate 6. All right. So this in water gives blue of this. All right. It turns to blue of this. And I told you now that when this is blue, what it means is that it contains hydrogen. All right. So now then, if you're being told to also test for nitrogen, so we can actually detect nitrogen ion in a sample by what we call the Prussian blue test. It's called Prussian blue test. All right. So the basic thing that we need to understand is that, okay, in this case now, there are different steps. Okay, there are different steps, but a Prussian blue precipitate or coloration indicates that nitrogen is present. All right, after you have been able to detect the presence of a nitrogen ion. All right, how do you detect the presence of nitrogen ion? Now you boil iron 2 salts. You boil iron 2 salt solution. Now when you boil iron 2 salt solution, okay, it produces what we call iron 3 hexacyanoferrite 2. Okay, and now this then gives you a blue coloration. So when it gives you a blue coloration, then it is meaning that nitrogen is present in that particular compound. All right, but you must boil this with the organic compound. When it gives you this and it gives you a blue product, a blue precipitate, then it means that nitrogen is present there. All right, then I told you that the test for halogens, okay, the test for halogens is actually done using the Lassine test. The test for halogens, the test for also nitrogen, and the test for sulfur. All right, but this is a special test to determine nitrogen. All right, this is a special test to determine nitrogen. All right, so now quickly we'll be looking at empirical and molecular formula. Okay, so this is a very common question that has to do with empirical formula. All right, so this question is very paramount, and of course it is a question that you should take note of. All right, so it's a repeated question. You can put it down. What is the empirical and molecular formula of a compound that contains 40% carbon that contains 40% carbon, okay, comma, 6.7% hydrogen and 53.3% oxygen. This is a frequently asked question, all right? Then by mass, okay? Now the molecular weight of in here is 180 grams per mole as given in the question. Now, basically, when you want to calculate empirical formula, you create a table. Now you create a table. Now this table now would have the elements here. So the elements here are carbon, we have hydrogen, and we have oxygen as well. Now what you're going to solve here are things that will enable you to get empirical formula, not molecular formula. You have to get empirical formula first. Now the mass is here. The mass is here, presented by masses here. For carbon is 40, for hydrogen 6.7, and for oxygen 53.3. Now, the first thing you need to do is to calculate the number of moles. Now, formula for number of moles is mass divided by molar mass. Okay. Now, the mass of carbon here is 40. Molar mass of carbon is 12. So 40 divided by 12 will give us 3.33. The mass of hydrogen here is 6.7. 6.7 divided by molar mass of hydrogen will still give us 6.7. The mass of oxygen is 53.3. Divided by molar mass, which is 16, will give us 3.34. Now, the next thing to do now is to divide by the smallest mole. Divide by the smallest mole. So among all of these, the smallest mole here, 3.33, 6.7, 3.34. The smallest mole here is 3.33. So you divide everything by 3.33. 3.33 divided by 3.33. 6.7 divided by 3.33. And 3.34 divided by 3.33. So this will give us 1. This will give us 2. Why this will give us 1 as well. All right. So it means that your empirical formula here, carbon is 1. There's no need writing C1. Hydrogen is 2. Oxygen is 1 as well. So the empirical formula is CH2O. CH2O. Now, how do we now calculate the molecular formula? Calculating the molecular formula is another easy step. It's another easy step. Now, but I told you that you must calculate the empirical formula before you calculate the molecular formula. Now, how do you calculate molecular formula? All right, molecular formula has its own technique. Molecular formula, MF is equal to EFN. What is N? N is the ratio of your relative molecular weight and your formula weight. So molecular weight and formula weight, or molecular mass and formula mass, the same thing. Now, so the molecular weight in this question, we were given 180 grams per mole. Now, molecular formula weight is from your empirical formula. Carbon is 12, more like you adding the molar masses of the substituent elements in the empirical formula. Carbon is 12, hydrogen is 1, but there are 2 hydrogens here, so 1 times 2. So you must take cognizance of the number of that particular atom. If carbon were to be 2 here, we would have done 12 times 2, but it's just 1, so it's 12 times 1, which is 12. Hydrogen is 2, 12 plus 2 is 14. Then 14 plus 0, 14 plus that of O, which is 16. Okay, 14 plus 16 will definitely give us 30. All right, so it means that we have 180 divided by 30 grams per mole. Grams per mole will cancel grams per mole. So 180 over 30 will give us 6. So this is our N. So it means that what do we do now? We would say our molecular formula now will be, what is our empirical formula? We are following this now. Empirical formula is CH2O, then times 6. So multiply 6 into here. So this will be C6. H2 times 6 is 12. Then O6. This is our molecular formula. All right. C6, H12, O6. And we know that this is, in fact, type it in the comment box. This is a very popular compound. All right. Type this compound in the comment box. All right, if you know what this compound is, don't browse it too. If you're a science student, you should know what this compound is without even browsing it. All right, so that is that. So now let's look at the next question. An unknown organic compound weighing 6.5 milligrams gave on combustion. Now the unknown organic compound, let's call it A. Okay, it weighs 6.5 milligram. It gave on combustion 20.47 milligram of CO2 and 8.36 milligrams of H2O. Now, one thing I must let you know is that combustion reaction is the process by which an organic compound burns in the presence of oxygen gas to liberate carbon dioxide and water. All right, only. So when an organic compound burns in the presence of oxygen gas and carbon dioxide and water are produced, that is a combustion reaction. All right, so now the question here is, first of all, I say calculate the percentage composition. Calculate the percentage composition. Then I calculate the empirical and molecular formula. Calculate the empirical and molecular formula if the molecular weight is 86 grams per mole. All right, so now we'll be solving this quickly. Now this is looking a little bit different from what we solved initially. It's looking a little bit different from what we solved initially, because here, instead of giving the mass of carbon, hydrogen and oxygen, we are now giving the mass of compounds instead of elements. Okay, what that tells you is that you will now have to get the mass of carbon from carbon dioxide, the mass of hydrogen from water, then the mass of oxygen from both carbon dioxide and water. All right, but it is not going to be difficult. Trust me, it's not going to be difficult. All right, I've explained it in one of my videos, the introduction to organic chemistry. I demystified the concept of molecular and empirical formula of organic compounds. All right, so now let us provide the solution to this. But now the first thing we are told to look to solve for is the percentage composition. Okay, percentage composition. But we cannot solve for the percentage composition when we don't know the actual mass of carbon, of hydrogen and oxygen. Now, how do you know the mass of an element in a compound? So mass of elements in compound, very simple. All right, so the formula for this is equal to, first of all, the mass, okay, the molar mass of elements, in compound divided by the molar mass of compound okay, then all multiplied by all times the mass of compound. This is the formula. So first of all, you have to divide the molar mass of the element in the compound by the molar mass of the compound. Then multiply everything by the mass of the compound. All right, so take note of that formula. So now it's important for you to note that this formula applies to you getting carbon, you getting oxygen, and you getting hydrogen. All right, but getting oxygen is a little bit different, a little bit dicey, but it's still not difficult, I promise you that. Now let us first of all look for the mass of carbon. Now let us look for the mass of carbon. So let me divide this into 3. Let's use here to look for mass of carbon in CO2. Now the formula is this: molar mass of elements in compound. What is the element you're looking for? Carbon, right? Now what is the molar mass of, the reason why I say molar mass of element in compound is because we must be particular about the molar mass of the element as regards to how many times the element appeared in the compound. All right, so the element here is carbon, and carbon, molar mass of carbon is 12. Okay, now molar mass of carbon is 12, but carbon appeared just once, so it will still be 12. All right, so the molar mass of carbon in the compound, if carbon were to be 2 here, we would have done 12 times 2, but carbon is just 1. And it's only from CO2 that we can get the mass of carbon. That's why we are using carbon dioxide. It's only from water that we can get hydrogen. So when we want to look for the mass of hydrogen, we will use water. All right, so the molar mass of the element in compound divided by the molar mass of the compound itself. The molar mass of carbon dioxide is 12 plus 16 times 2. Carbon is 12, oxygen is 16 times. So this will be 12 plus 32, which will give us 44. So we have 12 over 44, then times the mass of the compound. The mass of the compound is what you multiply this time. The mass of carbon dioxide given in the question is 20.47 milligrams. All right, so if you divide 12 by 44 and you multiply, okay, by 20.47 milligrams, now you have 5.58 milligrams of carbon. So this is the mass of carbon in the compound CO2. Now let's look for the mass of hydrogen in water, another very important thing. Now, like I told you, the molar mass of the element in the compound, which element are we considering? We are considering hydrogen. And hydrogen here, and molar mass of hydrogen is 1, but hydrogen is 2 here. So 1 times 2 will give us 2, divided by the molar mass of water as a whole is 18, while the mass of the compound water here is 8.36 milligrams. If you multiply this, you'll be getting 0.929 milligrams of hydrogen. All right, so now we have gotten for carbon and for hydrogen, and we are being told that the organic compound has a mass of 6.5 milligrams. And this organic compound, this 6.5 milligrams, 5.58 is inside, 0.92 is also inside, 0.929 is also inside. And the elements, we are being told that the elements for, in fact, in a combustion reaction, there are only 3 elements that can actually be produced. The elements can only be carbon, hydrogen, and oxygen. So what do? We say, okay, that now, we have now known the mass of these two, and we are saying that these two now are inside here. So if oxygen is also here, it means that if you add these two, what will remain from here will be for oxygen. So how do we do that? We'll now say the mass of A. We say mass of A, okay, mass of A minus, bracket open, mass of C plus mass of H, bracket close. All right, so this will be mass of A. Mass of A is 6.5 minus, bracket open, your mass of C is 5.58 plus 0.929. By the time you do this maths, by the time 6.5 minus this, your final answer will be 0. What it means is that oxygen is not in the compound. It means that oxygen was completely used off. All right, but it's not as if oxygen will always be 0. Please, it's not a standard. Oxygen can give you, in another question, oxygen can give you a particular value, but this is the way you would get the mass of oxygen. So this is the way you get the mass of O. All right, as long as you have gotten the mass of carbon and the mass of hydrogen, it's not supposed to be difficult for you to get the mass of oxygen now. All right, so now that we have known the masses, the different masses, now let us go ahead to solve for the percentage composition. Percentage composition was the first thing we are told to solve for. All right, so now we have to solve for the percentage of carbon. Percentage of carbon, now how to get percentage composition? We say mass of carbon divided by the total mass times 100. Now, what is the total mass? The total mass is the mass of A. We are trying to know the composition of carbon in our 6.5 milligrams of A. All right, I'm just using A to denote the compound because they not tell us what the compound is. All right, so the mass of C here, the mass of C that we got was 5.58 milligrams. Now, if you divide it by 6.5 milligrams and multiply it by 100, your answer will be 85.8%. This is a large percentage. All right, this is a large percentage. Now, if you want to do the same, percentage of hydrogen, okay, percentage of hydrogen now will now be the percentage of hydrogen now would be the mass, all right, of hydrogen that we got, which is still following this trend, mass of the element divided by total mass. So percentage of hydrogen will be 0.929 milligrams, which is the mass, divided by the total mass is 6.5 milligrams. We will multiply by 100. Remember, milligram will cancel milligram, just like here as well. Then when we do that, we'll have 14.2%. All right, 14.2%. If you add these two, you'll be getting 100%. You're getting 100%. There is no oxygen, right? There's no oxygen. All right, so now for us to now calculate the empirical formula, okay, for us to now calculate the empirical formula, we would use the same pattern we used in the first example to do this. All right, okay, so in the first example, okay, remember I told you that you draw something like this. Write the elements. Here we have just carbon and hydrogen. All right, now remember, the first thing you have to state their masses. Okay, we can use their main mass. We can also decide to use the percentage by mass. It's still fine. Now that we have the percentage by mass, let's just use it. So we have 85.8. If we use the normal mass, so trust me, we'll still get the same answer. All right, so 85.8 and 14.2. These are percentage by mass. The next thing is to calculate number of moles. Number of moles, I told you, is mass over molar mass. Mass all over molar mass. All right, so the mass here is 85.8. If we divide it by the molar mass of carbon is 12, it will give us 7.15. 14.2. Molar mass of hydrogen is 1. 14.2 as well. All right, then now the next thing now is to divide by smallest mole. So divide by smallest mole. The smallest mole here is 7.15. So we say 7.15 divided by 7.15. This will give us 1. 14.2 divided by 7.15. This will give us 2. It means that the empirical formula here is simply CH2. So CH2 is the empirical formula. I told you now to get molecular formula. Molecular formula is equal to empirical formula, then N. How do you get N? N is your relative molecular mass divided by your formula mass, or relative molecular weight, or molecular weight, anyhow you want to call it, divided by formula weight. All right, so relative molecular weight that was given to us in the question, okay, was, I think, 86. All right, was 86. Okay, so 86 now divided by the formula mass of CH2 carbon is formula mass is the molar mass of your empirical formula. Please don't forget that. So 12 plus 2 will give you 12 plus 1 times 2 will give you 14. So 86 divided by 14, your answer will be 6. All right, so it means that your molecular formula would be CH2 times 6, which will be C6H12. C6H12 is, okay, I gave you the other one as an assignment. Okay, let me tell you this one. This is hexene. This hexene. So the molecular formula helps you to actually know the elements. The molecular formula is the actual formula of an element. All right, it's the actual formula of an element. Sorry, a compound rather. Molecular formula gives you the actual number of moles, okay, of the elements, but it gives you the actual formula of the compound. So this is H12. This is a compound known as hexene. This is an alkene. All right, this is an alkene. All right, so how is molecular mass determined? Okay, so we are done with empirical and molecular formula, but it's important to know how molecular mass is determined. All right, so the determination, if you're being asked, the determination of molecular weight is mainly done by physical methods, and these physical methods are 4. All right, these physical methods are 4. So the methods are, firstly, by boiling point. All right, secondly, by freezing point. Secondly is freezing point. Okay, and freezing point. Then we also have vapor density. Vapor density is another way of determining molecular weight. Then we also have what we call mass spectroscopy. Mass spectroscopy. So these are the 4 major methods of determining the molecular mass of a compound. All right, of determining the molecular mass of a compound. Now, it's also important for us to note that the physical methods employed in determination of molecular weight of a compound also have other names also. All right, so this boiling point is also called ebullioscopy. Okay, it's also called ebullioscopy. So it's spelled Abullioscopy. Ebullioscopy. While freezing point is also called cryoscopy. 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 So if they can ask you, like I think 2019 2020 past question, they asked mention two physical methods employed in determination of molecular weight of a compound. All right, so you can say ebullioscopy and cryoscopy. That's fine. Okay, so that's fine. Now let's look at another way of identifying molecular compounds with molecular formula and all of that. So basically this particular identification is called IHD. IHD is known as index of hydrogen deficiency. Index of hydrogen deficiency, IHD. All right, so IHD is used to calculate the level of saturation or saturation of a compound. All right, but it is basically to know the hydrogen deficiency. Deficiency means lack. So how is hydrogen lacking in that compound? That is the major interest. So I'll give you a very shortcut formula that would help you to navigate through the calculation of index of hydrogen deficiency. And that formula is IHD equal to 2C minus H minus HAL plus Y plus 2 all over 2. All right, plus Y all over, or plus 2 all over 2. This Y, you can also represent it as N. Now let me tell you what this means. C is number of carbons. C is number of carbons. H is number of halogens. Sorry, number of hydrogens rather. Number of hydrogens. All right. HAL is number of halogens. All right. Then this Y I wrote here, or N, is number of group 5 elements. Group 5 elements are called nitrogen family. That's why I said N. All right. Then of course plus 2 over 2. These 2 and 2 are like fixed. Okay. So now it helps us to know the number, like I said, the number of carbon atoms that are lacking in an organic compound. All right. Sorry, hydrogen atoms. My bad, please. My bad. Okay. Please, slip of tongue. Hydrogen atoms, not carbon atoms. All right. So please, let's be together. I believe you're getting it. You're getting it. So this is a shortcut formula that will help us. All right. So it helps to determine the deficiency of hydrogen. All right, so now let's look at the question that will guide us through. All right, so this question is, they are being to calculate the unsaturation equivalence in the compound C8H8O2. That is, you should determine, when you say unsaturation equivalence, they are saying calculate the IHD, index of hydrogen deficiency of this. All right, so in this question now, let's quickly solve this. Now, number of carbons, remember that IHD, I told you, is 2C minus H minus HAL plus Y plus 2 all over 2. All right, all over 2. Okay. Now, so to solve this, carbon here is 8. So this will be 2 times 8 minus, how many hydrogens are here? 8 as well. Is there any halogen? I told you halogens are group 7 elements, which are halogens. Okay, those are halogens: chlorine, bromine, iodine, fluorine. These are examples of halogens. All right, so minus halogen, there's no halogen here, so let's say minus 0. Any group group 5 element, no, there's no group 5 element, there's no nitrogen here. Okay, there's no nitrogen, so that's 0. Then oxygen is not actually counted when it comes to IHD. Oxygen does not bond to hydrogen. Oxygen does not bond to hydrogen, so it does not cause unsaturation. It does not. So then plus 2, all divided by 2. So 2 times 8 is 16. 16 minus 8, all of these 0, 0, then plus 2 all over 2. 16 minus 8 is 8. 8 plus 2 is 10. So 10 over 2 is equal to 5. So our IHD here is 5. IHD here is 5. All right, so I believe that is clear. Okay, let's look at another question on IHD. Let's look at another question on IHD. All right, so it will be clearer as well. It will be clearer as well. Now for this question, this question says determine the IHD of C7H8ClN. all right, now how many, so let's determine IHD. How many carbons are here? 7. So we say 2 times 7 minus 8. Any halogen here is a halogen, so we say minus 1. How many is there in nitrogen family? Here is a nitrogen plus 1, then plus 2, all divided by 2. So 2 times 7 is 14. 14 minus 8 plus 1 minus 1 plus 1 is 0. So we have plus 2 all over 2. 14 minus 8 is 6. All right. So 6 plus 2 is 8. So 8 over 2 is actually 4. So our IHD is 4. All right. So please try this on your own. Determine the IHD of C7H6FNO2. So try this particular exercise on your own. All right. So that is that for that. These are frequently asked questions for index of hydrogen deficiency. All right. So we'll be looking at frequently asked questions on that bond characteristics and hybridization. All right. So now the first question we'll be looking at here is the average energy required to break all bonds in a compound is called dash. So the answer to that is bond energy. Is called bond energy. Bond energy is defined as the average energy required to break all bonds, whether it is a single bond or whether it's a double bond or whether it's a triple bond. All bonds can actually be broken when there is an effective bond energy. All right. So there's also what we call dissociation energy. So you say dash is the amount of energy needed to break a particular bond in a molecule in the gaseous phase. So when there is a bond in a particular molecule that is in the gaseous phase, the bond that is actually broken would require an amount of energy called dissociation energy. It's called dissociation energy. So that's another exam question. Now, another question is this. Okay, now the hybridization of the central carbon in CH3C, then triple bond N, and the bond angle CCN are A sp2 180 degrees, B sp 180 degrees, C sp2 120 degrees, and D sp3 109 degrees. Now it's very important to note. Now, first of all, the answer is B. Now, why is the answer B? The answer is B because this central atom has a triple bond. Okay, so when for triple bonds, their hybridization is sp, while their bond angle is 180 degrees. This is when it comes to hybridization. All right. So now let me explain hybridization, the concept of hybridization better. Okay. So now if you're being asked what hybridization is actually defined as the phenomenon of mixing up or merging of orbital of an atom of nearly equal energy, giving rise to an entirely new orbital equal in number to the mixing orbital and having same energy contents and identical shapes. All right. So the phenomenon of mixing up an old orbital, all right, an old orbital, okay, of an atom, okay, thereby giving rise to a new orbital, okay, which has the same number and the same energy and the identical shapes as the old one, is called hybridization. Okay, so it's the mixing up of old orbitals to form new orbitals. That's a very simple definition of it. So when two or more orbitals are actually mixed up to form a molecular orbital, the molecular orbital is the new orbital, but the thing is that nothing will change, only that the other one is old, this one is new. So if you're being told to define hybridization, that's how you define hybridization. Now it's also important to note that the concept of hybridization helps us to understand why carbon can make use of its 4 valence electrons, okay, for bond formation. And of course, there are 3 forms of hybridization. We have the sp3, we have the sp2, and we have the sp hybridization. Let me just quickly summarize what sp3, sp2, and sp is. Now, sp3 hybridization is actually composed of two s orbitals, okay, two s orbitals and two p orbitals. All right, so these are like old orbitals. Okay, so when these two orbitals are like mixed, now basically sp3 hybridization is formed. But now that is not the major thing. The major thing is that when it comes to sp3 hybridization, sp3 hybridization has what we call a tetrahedral shape or a tetrahedral structure, something like this. Can have something like this. Then we have hydrogen here, we have another hydrogen here, we have another hydrogen here, we have another hydrogen here. This is what we mean, the bonding. This is what we mean by tetrahedral. CH4, like this, is called what we call methane. We know it as methane. It's the first member of the alkane family. Okay, now it has a bond angle of 100. The bond angle here is 109.5 degrees. All right, that is the bond angle. So examples of elements that exhibit this sp3 hybridization I talked about are alkanes. So all alkanes exhibit this sp3 hybridization, and they are all single bonds. That's one thing you must take note of. They are all single bonds. All right, so the bond angle between each bond is 109.5. Between this bond and this bond, 109. Between this bond and this bond, 109.5. Now let's look at sp2 hybridization. So basically, this sp2 hybridization has to actually do with double bonds. All right. So with double bonds. So it's more like something like this carbon double bonded to another carbon. Then we have two hydrogens. We have hydrogen here, we have hydrogen here, we have hydrogen here, we have hydrogen here. Okay, something of this nature. This is a typical example of the sp2 hybridization. This is the second type of hybridization. If you look now, you have a double bond here. Then of course carbon here, single bonded to hydrogen to hydrogen to hydrogen. So these are usually found in alkenes. They're usually found in alkenes. All right. So this shape here for sp2 hybridization, this shape, just like, remember I told you that for sp3 they are called what? It has a tetrahedral shape. All right. For sp2, okay, first of all, the bond angle here is 120 degrees. The bond angle here is 120 degrees. It's 120 degrees between the different bonds. Why the shape is called a trigonal planar shape. Okay? Trigonal planar. All right? Or planar, as you may pronounce it. So this is the shape. Okay? Then the third one, which of course came from the question that we just solved here, is called the sp hybridization. So for sp hybridization is actually exhibited among alkynes, that is triple bonds. Exhibited among alkynes, that is triple bonded organic compounds. And one thing we must take note of is that the bond angle for this, like I said, from this one we looked at, this particular question we looked at, for triple bonds is 180 degrees. That's the bond angle. All right, so we'll see something like this: C triple bonding to C, then we have H here, we have H here. All right, so this is a typical example of what we are talking about. So it has 180 degrees, okay, and this is called a linear shape, more like linear relationship. All right, so this shape is actually linear because it's just in a straight line. All right, so this is a linear structure. All right, this is a linear structure. So I just had to take my time to just run through this and explain this. All right, while we also proceed with the frequently asked questions. All right, while we proceed with the frequently asked question. So now, another question now you might be asked is this: okay, how to determine pi and sigma bond determination. All right, how do you determine the number of pi bonds and sigma bonds in an organic compound? Now let's look at a typical question. All right, say, okay, now let's look at this. Say the question is 3-methyl 1-pentyne contains the following combination of bonds. So A, sp3 and sp, B, sp3, sp2 and sp, C, sp3 and sp2, D, sp only. Now, one thing you need to understand is that 3-methyl 1-pentyne, all right, contains a triple bond in it, okay, as well as single bonds. So it has a triple bond in it as well as single bonds. Now the structure is like this: CH3, CH2, CH, then we have C, then triple bond like this. This is CH. Then maybe then at carbon 3, 1, 2, 3, at this carbon we have CH3. All right, we have CH3 at this carbon, at the third carbon. So now this is 3-methyl 1-pentyne. It's called 1-pentyne because the triple bond is at carbon 1. Mind you, this triple bond can be at this carbon, but the thing is that when you are counting, you count from the carbon. That's why we say 3. We do not count from here 1, 2, 3. We do not. Although if you count from here, it will still be 3. But if you count from here 1, 2, 3, 4, the double bond will now be at carbon 4, so it will be 4-pentyne. But it is wrong. You don't count from the sides that will not give the double bond the smallest, the double or triple bond. This also applies to double bonds. So you must count from the carbon that will give the triple bond the smallest possible number. So if you look at it now, you have single bonds and you also have triple bonds. All right, so it means that it contains sp3 and sp. sp3 is for single bonds, sp is for triple bonds. So that's the answer. So now let us now look at a question. Let's look at a typical question. Now they say how many sigma bonds. Now let's look at sigma and pi bonds determination proper. All right, so if at this point you've not subscribed, please go back and subscribe. Also like this video if you are gaining knowledge from the video. Now, so how many sigma bonds and pi bonds are present in a molecule of propene? Okay, so you know propene. Now propene is an alkene that has a double bond. Of course, alkenes have double bonds. An alkene that has three carbons. All right, so the first thing you have to do in order for you to actually know the number of sigma bonds and pi bonds is to draw the structure. Now the structure of propene is CH2, double bond CH, then single bond CH3. You know propene is C3H6, right? C3H6. Now after you have done that, this is the normal structure. Then now this structure, now it means that of course carbon here has a double bond, then has 2 hydrogens, then is bonding to another carbon that has 1 hydrogen and another carbon that has 3 hydrogens, hydrogen, hydrogen, hydrogen. Now one thing I need you to understand that all sigma bonds, okay, are found in both single bonds and double bonds. All right, so let me just rephrase it. Okay, all single bonds are sigma bonds. All single bonds are sigma bonds. Take note of that. All single bonds are sigma bonds. Then in every double bond, there is 1 sigma and 1 pi. In every double bond, there is 1 sigma and 1 pi. So if you look at this structure now, you realize that we have 1, 2, 3, 4, 5, 6, 7 single bonds. So it means that in all the single bonds, there are 7 sigma bonds. Remember, I told you all sigma bonds are all single bonds rather are sigma bonds. There is no pi bond in a single bond, except the bond is a double bond. Then it will have 1 sigma and 1 pi. Okay, take note of that, please. All right, so take note of that. But now another thing you need to understand is that okay, before we get there, let's just finish with this. We'll look at another question that has a triple bond so I can explain to you that concept. Now, so it means that we have 7 sigma bonds plus the 1 here, so that is 8 sigma. Then the 1 pi bond here is 1 pi. So it means that in this structure we have 8 sigma bonds and 1 pi bond. That's what it means. 8 sigma bonds and 1 pi bond. Please don't forget that all single bonds are sigma bonds, and in a double bond, 1 is sigma and 1 is pi. Okay, now let's look at another question. Say, how many sigma bonds are present in 3-pentyne? 3-pentyne. Say, how many sigma bonds are present in 3-pentyne? Now, 3-pentyne is actually pentyne in which the triple bond is at carbon 3. Okay, the triple bond is at carbon 3. So carbon, okay, the triple bond is at carbon. Pentyne is 5 carbons now. 1, 2, 3, 4, 5. So we are saying that the triple bond is here at this carbon. 1, 2, 3. So it means that here now we have single bond. Here we have single bond. Here we have single bond. Now this carbon will be 3 hydrogens. This carbon will be 2 hydrogens. This carbon now will not have any hydrogen left because it has 4 bonds now. The 4 bonds have collected all the 4 hydrogens. This carbon will also have 4 bonds. So then this one has only 1 bond. So it means that 3 hydrogens remain. You know the general molecular formula for alkynes. Okay, general molecular formula for alkynes is CnH2n minus 2. So if we say if we for pentyne is normally pentyne is C5. Then H2 times 5 minus 2, which is C5. H2 times 5 is 10. 10 minus 2 is what? 8. C5H8. Okay? It's 3 plus 2, 5 plus 3, 8. Alright, but that's not even the major thing here. The major target here is to be able to calculate the number of sigma bonds. Now let us draw the naked structure of this containing all the bonds, the carbon to hydrogen bonds. Now carbon, now we have 3 hydrogens here. Hydrogen, hydrogen, hydrogen. Now this carbon has 2 hydrogens. Hydrogen up, hydrogen down. This carbon has no hydrogen. It has a triple bond. This carbon has no hydrogen. Double bond to carbon, hydrogen, hydrogen, hydrogen. All right, you've seen it, right? So now, first of all, remember I told you that all the single bonds are sigma bonds. So now let's count the single bonds first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10. So 10 from the single bonds, 10. Now let me explain this to you. Now in a triple bond, for a triple bond, okay, take note of this. For a triple bond, we have 1 sigma bond and 2 pi bonds. Please don't forget that. 1 sigma bond and 2 pi bonds. So it means that now, remember we have counted 10 sigma bonds initially, right? So we have counted 10 sigma bonds initially. So plus the one that is in this triple bond. So it means that sigma bond here is 11. 10 plus 1, 11. Then pi bond is, although we are not told to count the number of pi bond, but I'm just explaining it for you just in case. Okay, pi bond 2. Remember, in a double bond, we have one sigma and 1 pi. But in a triple bond, we have 1 sigma and 2 pi. Okay, please take note of that. But in a single bond, all of them are sigma bonds. All are sigma bonds. All right. So you try this. You determine the number of sigma and pi bonds in 2,3-dimethyl hexane. All right, so determine this and write your answer in the comment box. All right, 2,3-dimethyl. This is a typical exam question. All right, so now we'll be looking at frequently asked questions under isolation and purification of organic compounds. Isolation and purification of organic compounds. We'll be looking at frequently asked examination questions under here. All right, so now the first question we'll be looking at now: what is the separation technique that is used for liquids that dissolve in each other and have a very close boiling point? So that the answer to that is called fractional distillation. fractional distillation. Take note of that. Another question: the laboratory instrument used to prepare liquid immiscible. Immiscible is spelled this way: liquid immiscible mixture. That is liquid mixtures that you combine liquids together that cannot be mixed completely. All right, so what is actually used to separate such mixtures? All right, it is called a separating funnel. So it's called a separating funnel. It's a separating funnel that is actually used for that. Now, when water is added to hexane in a separating funnel, what is the liquid in the upper layer? All right, so when you add water to hexane in a separating funnel, okay, a liquid comes up in the upper layer. All right, now let me just explain this. Now, in a separating funnel, the less dense liquid, that is the lighter liquid, that is liquid that is not heavy. The lighter liquid is the one in the upper layer, whereas the heavy one is the one in the lower layer. So therefore, hexane is less dense than water. All right, hexane is less dense. It is lighter than water. So because of that, it will be the liquid at the upper layer because it is less dense, while water will be at the lower layer. So it means that hexane would actually be the one at the upper layer. Please take note of that particular explanation. Now, then another question: crude oil can be separated into useful products by fractional distillation as well. So it's fractional distillation that is used to separate crude oil. All right, so now another question. This is a calculation question. Now, in a laboratory setup for paper chromatography is another process of separation. Now, if a component traveled 4 cm, and the solvent traveled 10 cm, calculate the ROF value. All right, so ROF value is actually used to test the ratio of the distance that the spot moved, or the component moved, to the distance that the solvent moved. All right, so now it's just simply the distance of the distance spot moved. Okay, ROF is just the distance spot moved, okay, divided by the distance solvent moved. So this will just be 4 divided by 10. That will give us 0.4. All right, it doesn't have a unit. So 0.4 is the answer. It doesn't have a unit. Okay, so take note of that. Very important to note. Okay, now we'll be looking at another question. Now, give any 3 types of chromatographic techniques. All right, now 3 types of chromatographic techniques. We have paper chromatography. We also have gas chromatography, and we have column chromatography. So these are 3 major types of chromatographic techniques. Okay, so now mention one parameter that is used to determine the purity of a solid. If you want to determine the purity of a solid, what is one parameter that can be used? Now, basically, the answer is melting point. Now, how? Pure solids actually melts at a very fixed melting point and not a range of value. So it's not a range of value that pure solids melt. They melt at a fixed, the key word there is fixed melting point. So it is melting point that you actually use to actually determine how pure a solid substance is, especially a solid organic compound. Okay, now let's look at structural determination and identification. All right, structural determination and identification. Okay, now basically there are different types of ways of determining the structure of an organic compound and identifying it as well. Now, there's what we call spectroscopy. All right, the 3 major. Okay, let me give you a question. Now, give the names of the 3 major spectroscopy techniques used to identify an organic compound. Now, these major spectroscopy techniques, number 1 is what we call the infrared spectroscopy. Infrared spectroscopy is called IR spectroscopy. Number 2 is what we call the NMR, and NMR is called nuclear magnetic resonance. Nuclear magnetic resonance spectroscopy, which is NMR. Then another one is what we call the ultraviolet ultraviolet spectroscopy, which is called UV, ultraviolet spectroscopy. All right, so now basically all these spectroscopy techniques have their different functions. Okay, I'll just be summarizing the functions of these spectroscopy techniques quickly. All right, so for the first one, which is infrared spectroscopy, now it gives information on the type of functional groups present in a molecule. All right, for instance, now if we have let's say methanol is CH3OH. Now the functional group that is here is called, this is an alcohol. Okay, this is an alcohol. So infrared spectroscopy helps in determining the type of functional group present in a molecule. Okay, now the second one is nuclear magnetic resonance. So this one gives information on the number and nature of carbon atoms present in an unknown organic compound. So the most common ones are, of course, the most common types of nuclear magnetic resonance, okay, are of course the proton magnetic resonance spectroscopy and the carbon-13 proton NMR and carbon-13 NMR. These are the types of NMR. So please don't forget that the major function is that it helps you to know the number and nature of carbon atoms, okay, present in an unknown organic compound. Then of course we also have ultraviolet spectroscopy. Ultraviolet spectroscopy is used to detect the presence and nature of multiple bonds between atoms, okay, between atoms. So it is used to know the presence and nature of multiple bonds that are between atoms in an organic compound. Then there's another one. This one is not so common. It's called mass spectroscopy. Mass spectroscopy. What is mass spectroscopy used for? It gives information about the relative molecular mass of a compound with a very high degree of precision. All right, the very high degree of precision. So it gives that kind of information. It helps you to know more like a very accurate or precise molecular mass of a compound, particularly an organic compound. So that is called mass spectroscopy. So these are like the 4 spectroscopic techniques. Okay, so please do not forget that. All right, do not forget that. They are very, very important. These are very, very important exam focus areas, all right, on identification. Okay, so now that's it. Okay, now let's look at questions under isomerism. Questions under isomerism. All right, frequently asked questions under isomerism. You know what isomerism is now? Isomerism is actually a phenomenon in which compounds have the same molecular formula, but they have different structural formula. All right, so basically isomerism, I did an introduction on that in one of my videos on this channel. All right, so isomerism is divided into two. Majorly we have structural, and we have another one. We have what we call stereoisomerism. Now under structural we have the chain, we have positional, and we have functional. Under stereoisomerism we have geometrical, and we have optical isomerism. All right, so basically this is the major classification of isomerism. So we'll be looking at questions that would help us to best understand the concept of isomerism. Okay, now the first question we'll be looking at, this question says underline the compound that exhibits geometrical isomerism. Okay, that exhibits a geometrical isomerism. Now we have 2-butene, A 2-butene, B 2-butyne. There's a bond here. Between 2-butyne. Between 2 and B there's a bond. Then C 2-butanol. D none of the above. Now let me hear you this. Now butene, okay, butene exhibits geometrical isomerism is more like a form of isomerism that occurs in space. It's a spatial form, SPATIAL is a partial form of isomerism. So more like, it looks more like this, okay. Then we can have a structure like the CH3, then CH3 as well. All right. Whereas here we have H, and here we have H. This is a form of geometrical isomerism. Okay, we have two forms of geometrical isomerism. We have cis and trans. Okay, let me write it down here: cis and trans isomerism. Okay, so this is an example of, this is what we call trans butene. So this is trans butene. This is trans butene. Then if you want to, then for the cis now would be, now this trans, because this CH3 here opposite. Why is it 2 butene? It's 2 butene because if you want to count now, it will be 1 2. The double bond is a carbon 2. It's not 1 2. Even if you count from here, it's still 1 2. This double bond will be a carbon 2. If you want to have more understanding of nomenclature of alkenes, watch my video on that. All right, it's also on this channel, how to name alkenes. Now, okay, now for trans, now for this trans, for cis now, we'll have still CC here, but now here this CH3 will be here. CH3 will also be at the top. Then you have our H, you have our H. This is what we call cis butene. Both of them are forms of geometrical isomerism. Both of them are forms of geometrical isomerism. All right, so please, very important to take note of that. Now let's look at another question. So what type of isomerism exists between ethanol and dimethyl ether? Now the answer to that is called functional group isomerism. All right, so the answer to that is called functional group isomerism. But now the question is, what kind of isomerism exists between ethanol and dimethyl ether? Ethanol and dimethyl ether. Now, functional group isomerism is a type of structural isomerism in which both of them have the same molecular formula, but the only difference is that they have different functional groups. That's what functional group isomerism. The positional isomerism is actually the same molecular formula, but different positions of the functional group. The same functional group, but the functional groups are connected to different carbons. All right, different carbon atoms. While for chain isomerism has to do with a structure. Chain isomerism is still under structural isomerism, but it has to do with a structural form of isomerism in which the what's it called? The carbons are actually arranged in different forms, different arrangement of carbon atoms in a chain. All right, that is for chain isomerism. All right. So basically, ethanol is from the alcohol group, dimethyl ether is from the ether group. Both of them have different structures, but they have the same molecular formula. That's why it's called functional group isomerism. All right, that's why it's called functional group isomerism. Okay, so basically, that is actually the understanding of isomerism. All right, you can also watch my video on introduction to isomerism to understand isomerism better. Okay, but these are possible questions or frequently asked questions under isomerism. All right, so now we'll be going straight into reactions. All right, we're going straight into reactions. Now, these questions under reactions, please take them very seriously. If you've not liked this video, like the video. All right, these questions under reactions, please take them very, very seriously. All right, so we'll be looking at frequently asked questions under organic reactions. All right, so basically, it's very important to note that reactions are majorly part of organic chemistry, and you cannot take them out of that. Okay, you cannot take them out of that. Now, the first kind of question now is this. Now, what kind of reaction takes place in the following equation? All right, so the following equation, let's say we have CH3Cl plus KOH to give us CH3OH plus KCl. All right, now this is a substitution reaction. All right, the Cl of CH3Cl, okay, went to meet KCl. All right, left to meet KCl. why the OH here was replaced. It's the OH here that was replaced with this on this product side. So it's more like an interchange. OH came here, Cl came here to give you this. So this is an example of a substitution reaction. So when there is a switching, when there is a switching in components on the product side, it gives a substitution reaction. All right. Now the reaction below belongs to what kinds of reaction? All right. So this kind of reaction where we have arrow CH2 CH2OH. All right. Then we have the catalyst to be concentrated H2SO4 here. Then we have product arrow CH, then double bond CH2 plus H2O. Now the question is, what kind of reaction is this? Now this is called a dehydration. This is called a dehydration reaction. Now how is this a dehydration reaction? The dehydration reaction because there is removal of alcohol. All right, there's removal of alcohol, that is OH, to form water here. You can see water. So OH is removed here. And now OH is removed from an alkanol. All right, but this alkanol you're seeing here, now when OH is removed from an alkanol, an alkene is formed. Okay, an alkene is formed. So this is a dehydration reaction. Dehydration reaction. So this is dehydration of, you can say dehydration of alcohols. Okay, dehydration of alcohols. Okay, now then another reaction is, let's say arrow CH2, then CH2, then we have X. Now in the presence of the catalyst NaOH and ethanol. Now what is formed here? Now we have arrow CH, then CH2 plus HX. All right, plus HX. Okay, plus HX. Now the question here is that what kind of reaction is this? Now this is what we call the hydrohalogenation of haloalkanes. Haloalkanes are actually alkanes that has halogens like this. This arrow now here can be CH3. Okay, for instance, now CH3, CH2, CH2. Then we can have Cl here. Now this is chloropropane. This is chloropropane. So when chloropropane is actually catalyzed by NaOH or ethanol, now as catalyst, now you will now have CH3, CH, double bond CH2. Now the reason why this double bond is here is because that is where chlorine was bonded to. So you place the double bond at the place where chlorine was, but the carbon that chlorine was bonded to, which was the first carbon here. All right, which was the first carbon here. Chlorine can be bonded to any carbon, but ensure that your product now, your double bond must be where your halogen was bonded. This can actually be bromine, it can be iodine, it can be any halogen at all. All right, but just know that now when your double bond is formed, plus your product here now would be this chlorine that was removed from here will come here now to form an acid, which is HCl. So this is the reaction. Now this is propene. This is propene, then this hydrochloric acid. This propene, then this hydrochloric acid. Okay, but this was chloropropane before. All right, this was chloropropane before. Okay, now the next one is, what class of reaction does the transformation? Like I told you, this is the hydrohalogenation of haloalkanes. Okay, so you can try this. You can try this. Say CH3, then CH, Br, CH2, CH2, CH3. So write the products for the dehydrohalogenation of this particular compound. Dehydrohalogen. Write the products for this. All right, write the product and drop your answer in the comment box below. All right, so and then now say what class of reaction does the transformation below belongs to? Now this is the transformation CH3, this is the reaction, okay, plus HCN. All right, then here now we have, of course, bonded to O, oxygen. Now this is the product. The product here is CH3CH, then the cyanide, then OH. All right, this is an addition reaction. So basically, addition reaction involves adding groups or atoms across the double or triple bond, thereby reducing the double or triple bond. Okay, so when you add groups or atoms to a particular compound, that has a double bond or a triple bond, and that double bond or triple bond reduces, for instance, if it was the triple bond and the triple bond reduces to double bond, or if it was a double bond and the double bond reduces to single bond, that is what we call addition reaction. So this is an example of an addition reaction. Look at this double bond here. It reduced to form a single bond here to OH. So this is an example of an addition reaction. So please take note of all of these. Take note of all of these. Now, if you look at all these reactions that we even did before, that we even did before, you realize that instead of the reaction now to actually reduce, it increased. Here was single bond, here became double bond. So the opposite of addition reaction now is when a single bond becomes a double bond, or when a double bond becomes a triple bond. That is an example. That is what we call elimination reaction. That's what we call elimination reaction. That is the opposite of addition reaction. All right, so take note of that. Okay, now then we have another question. Say, write an equation for the complete combustion of propane. Now, combustion reaction, the formula for combustion reaction is CXHY plus X plus Y all over 2 O2 to give us XCO2 plus Y all over 2 H2. Please, this is Y over 4. This is Y over 4. All right, so X plus Y over 4 O2 to give us XCO2 plus Y over 2. So we are told to write equation for the complete combustion of propane. Propane is C3H8. Remember, alkanes have general molecular formula CnH2n plus 2, where N is the number of carbons. All right, where N is the number of carbons. So now, take note of that. Now, so if we have C3, so now this is C3H8 plus, now X is your number of carbons, right? Y is your number of hydrogen. So this will be 3 plus 8 over 4 O2 to give us your X is 3 CO2 plus your Y is 8 over 2 H2O. This formula is very easy to memorize. Please don't forget it. All right, so we have C3H8 plus 3 plus 8 over 4 is 2 O2, 3 CO2, 8 over 2 here is 4, so 4H2. So the final reaction will be C3H8 plus 3 plus 2 is what? 5 O2 to give us 3 CO2 plus 4 H2O. This is the reaction. All right, so that is the reaction. So please take note of that. Don't forget that. So now we'll have other questions as well. We have other questions as well that we'll look at. So let us look at more questions under addition reaction of alkenes. Mind you, this reaction is combustion reaction. Please don't forget that. Excuse me. So now addition reaction of alkenes. All right. So please, I want you to note this question. Now, what is the name of the rule that governs the addition of protons to carbon with greater number of hydrogen atoms? All right. So that rule is called Markovnikov. Okay, Markovnikov's rule. All right, so it is the rule that governs the addition of protons to carbons with greater number of hydrogen atoms. All right, with greater number of hydrogen atoms. It's called Markovnikov rule. All right, so that's Markovnikov's rule. All right, so now another question is this. Okay, still under, of course, addition reaction of alkenes. Now, the question is, what is the product or reaction of propene with hydrogen bromide? Now, propene, propene is C3H6, all right, which is CH2, CH, then single bond CH3. This is propene, all right. So, like I said, if you are struggling with understanding nomenclature, this particular video, we are not focusing on nomenclature. We are focusing basically on reactions and, of course, the other aspects that we have treated. All right, watch my videos on nomenclature and get a better understanding of how to name organic compounds. Now, so what is the product of the reaction of propane with hydrogen bromide? Now, if propane reacts with hydrogen bromide, HBr, all right, now what will happen here is that this bromine here and this hydrogen here will now come, and it will now they will now be fixed in the carbons here. All right, hydrogen now will bond to one carbon, and thereby it would reduce the double bond. Remember, I told you that addition reaction has to do with when a particular bond is reduced. For instance, double bond reducing to single bond, or triple bond reducing to double bond, and most times it's as a result of addition of hydrogen. Most times it's due to addition of hydrogen. So when as hydrogen is present, immediately you introduce hydrogen here. Okay, now hydrogen now will reduce this double bond to single bond. So you will now have CH3. Okay, then you now have C. All right, you now have C here. This C now will be bonded to Br. Okay, this C will now be bonded to Br. Then we'll have CH here. Then we'll have CH3. So now, if you now look at it now, you have been able to form a single bond all through. You're able to form a single bond all through. All right. So this is a typical example of an addition reaction. This is 2-bromopropane. This is 2-bromopropane. All right. This is 2-bromopropane. Now the next question: give the laboratory test used to differentiate between pentane and pentene. Now the two tests that are used to differentiate between pentane and pentene, that is between the single bond pentane and the double bond pentene, which of course are alkane and alkene respectively. Those two tests are called bromine water test. And what another one we call the Bayer test. So these are the two tests that are used to differentiate between these two. All right, so these are the two that are used to differentiate between pentane and pentene in the laboratory. Okay, so the next question is, what is the product of the anti-Markovnikov addition of hydrogen bromide to propene? All right, anti-Markovnikov is more like, it's still the same question as this. All right, still the same question as this. Okay, but now in this case now, one thing we need to understand is that the Markovnikov rule. Okay, remember I told you Markovnikov rule has to do with the rule that governs the addition of proton to carbon with greater number of hydrogen atoms. All right, so now if you look at this particular reaction, okay, this particular reaction is called if you look at this now, let me show you something here. Now CH2 here, CH3, hydrogen now was added to this CH2. Are you seeing it? Hydrogen was added to this CH2, thereby liberating CH3 here, and of course CH here, then CH3 here, so a single bond all through. Okay, single bond all through. So the anti-Markovnikov rule now will be the rule where it will be an opposite of the Markovnikov rule. So it will be when the addition of proton is added to the carbon with the lower number of hydrogen atoms. All right, the lower number of hydrogen atoms, which is almost similar to this as well, only that it will be swapped. This Br now will go to another carbon, and this hydrogen will increase. Br can come here, and this will be CH2. Why this CH now will be CH2? Here will be CH2 as well. But both of them, it will still be the same number of carbons and the same number of hydrogens. But in that case now, that one will be 1-bromopropane. That one will be 1-bromopropane. All right. So now let's look at another question. Okay. So, all right. So this question says, draw the structure of the product of the reaction of CH3, CH2, CHC, CH3, and 2 with HBr. Okay, with HBr / CH3O, then 2, and name the compound. Now basically we have to draw this out first. Now this is CH3 to CH2 to CH. Then C now, we are being told that this C now has 2 CH3. That's what this in bracket means. Okay, that's 2 CH3. Then now plus HBr. Now this HBr now here, if you look at it very well now, you realize that we have this as CH3O, then 2. What this means is that this is a catalyst. So now what will be formed will be CH3, CH2, CHC, CH3. Then here we have CH3, here we have H, and here we have Br. Okay, so now we can call this 1, 2, 3. So this will be called 3 bromo. Okay, now if you check, if you now count from here, okay, no, you have to count from here because you're supposed to give it the lowest possible number. So so it will be, you're counting from here, 1, 2, 3, 4, 5. Longest continuous carbon chain is 1, 2, 3, 4, 5, which is pentane. So you realize that methyl now is at carbon 2, bromo is at carbon 3. Alphabetically, you start from bromo. So this will be 3 bromo 2 methyl pentane. All right, so this is the compound that is formed. Now, how did I come about this? What happened here was that I attached H here. I attached H here to one of the carbons here. Okay, I attach hydrogen here to one of the carbons here, this carbon in particular. Then bromine bonded here, bromine bonded here. Okay, bromine bonded here. But basically here we had a double bond. In this case we had a double bond here. Actually, we had a double bond here. Now, because you cannot, if you have CH here, there must be a double bond here before this will be CH, because here was supposed to be CH2. But the fact that there is CH here, it means that there is a double bond here. So that is what it should tell you. So I just had to come here. I just realized. So this was initially an alkene. This was initially an alkene. As a matter of fact, this was 1, 2, 3, 4, 5. 1, 2. This was 2 methyl. This was 2 methyl pent 1, 2 pent 2 in. All right. This was 2 methyl pent 2 in. The reason why it was 2, 1, 2, because the double bond. This double bond is at carbon 2. That's why it's 2 methyl pent 2 in. Okay, so 3 bromo 2 methyl pentane is what is formed. Is what is formed as a result of this reaction. This is still an addition reaction. Please, this is a catalyst here. Okay, we should catalyze this reaction. Okay, we should catalyze this reaction. So whenever hydrogen is added, please, I beg you, try and understand that if hydrogen is added here, it's an addition reaction, and the addition of hydrogen here will drop this double bond to form a single bond in this addition reaction. So that is very, very important to take note of. And another thing you must take note of is that this can be any, don't mind the fact that we have been using HBr. This can be anything. It can be HCl, it can be HI, it can be HF as well. It can be any halogenous acid. All right, so please take note of that. All right, so basically we would also be looking at some more critical questions before we look at the reactions of benzene. Now, what is carbon bonded to 4 carbon atoms called? Carbon that is bonded to 4 carbon atoms. Okay, to 4 carbon atoms. Carbon, 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 carbon. Okay, what is it called? Now, this carbon is called a quaternary carbon. It's spelled Quaternary, quaternary carbon. All right, so now also note that carbon bonded to one other carbon is called primary carbon. The one that is bonded to 2 is called a secondary carbon. The one that is bonded to 3 is called a tertiary carbon. For instance, now if we have, let's say, CH2, then here we have CH3, then here we have CH2, CH3, then here we have CH3, then here we have CH2, no, CH3, here we have CH3, then here here we have, okay, let's stop here, CH. Now if you look at this, now this carbon is bonded to 1, 2, 3, 4, so this carbon is called a quaternary carbon. Now this carbon here that is bonded to just one carbon is called a primary carbon. Now this carbon that is bonded to just 2 carbons is called a secondary carbon. Then this carbon that is bonded to 3 other carbons is called a tertiary carbon. All right, so that's what I mean. That's what I'm trying to explain. All right, so now questions under bond fission. Like I said, we'll come back to reactions of benzene. Questions under bond fission. Now, the process by which radicals are formed is known as homolytic. The type of bond fission in which radicals are formed is called a homolytic fission. All right, homolytic fission is also known as homolysis. All right. Now, the homolysis in chemistry leads to what the production. This homolysis leads to the production of dash. So it leads to free radicals. These radicals are not just radicals; they are called free radicals. All right. So now, when you call heterolytic, the heterolytic has to do with the formation of external radicals. All right, external radicals. So there is heterolytic. Now, assuming a heterolytic fission of a carbon-carbon bond in an organic compound, the species that are formed from heterolytic fission, they are called what we call carbocation and carbanion. Okay, carbanion. Okay, so this is called carbocation or carbocation, and this is carbanion. All right, carbocation and carbanion. Right, a mouthful actually. All right, so now then there are things we called electrophiles and nucleophiles. Electrophiles and nucleophiles. Now, basically, when we say electrophiles and nucleophiles, all right, so what are we implying? Now, reagents that attack a substrate at a position of low electron density are called nucleophiles. Okay, they attack a substrate at a position that there is low electron density, where the electron is light, where the electron is less dense. All right, so those reagents that attack the substrate at the position of low electron density, they are called the nucleophiles. While the reagents that attack a substrate at a position of higher electron density, they are called electrophiles. Now, that particular area of low electron density is an area where electrons are less active, while here electrons are more active at this point. That's why electrophiles. Electrophiles, from the word philes, means love. Electron. So they love electrons. So it is here that electrons are more active. That's what we call it high electron density. All right. So please take note of that. Very important to take note of. So now let us look at still this particular aspect that we were delving into initially, reactions of benzene. All right, reactions of benzene. Okay, so we'll be looking at nitration of benzene. All right, so nitration of benzene is more like the addition of tetraoxosulfate 6 acid. All right, tetraoxosulfate 6 acid. Then there is also an electrophile here. I'll be writing the reaction. All right, so when we have H2SO4 plus HNO3, all right, now it liberates NO2 plus HSO4 minus, and of course water. Now the electrophile here is NO2 plus, because this is the reagent that attacks the low dense area, the substrate at the low dense electron area. Remember, I defined what nucleophiles and electrophile. No, this one is for high. All right, I define the high dense is for electrophile. Nucleophile is for low dense. Please don't forget that. All right. Now, it's very important for us to understand also that H2SO4 here is a catalyst. All right, H2SO4 is a catalyst. So normally benzenes have the general molecular formula C6H6. All right, they look like this. Okay, let me bring it down. Let me draw it down. All right, so we have a bond here, a double bond here, another double bond here. So plus NO2 plus. Like I said, this is the electrophile. All right, so now it reacts now to form this nitration reaction. We have here. Then our NO2 is bonded. So this is what we call nitrobenzene. Now this is your benzene. All right, this is called nitronium. This is called nitronium. Like I said, this is an electrophile. Then the catalyst that speeds up this reaction is H2SO4. Now this reaction, they can tell you that you should write the reaction for the formation of the electrophile. Now this is the reaction for the formation of the electrophile NO2+. Why this is the reaction for the nitration of benzene. Alright, so like I said, Na2+ is the electrophile. It's also called the nitrating agent. It's also called the nitrating agent. Alright, also called nitrating agent. So this H2SO4 here is concentrated. It's concentrated H2SO4. Alright, it's concentrated H2SO4. Now, the nitration of benzene can also be written like this. Can also be written like this. Plus HNO3. Now, H2SO4. Then we have this. We have this. Then NO2. It can also be written like, in fact, popularly it is written this way. Popularly it's written this way. Now, this is the reaction to show the effect of the electrophile, which is a nitrating agent. All right, this is the reaction to show the effect of the electrophile. All right, so now another one is sulfonation of benzene. Sulfonation of benzene. Sulfonation of benzene. All right, so when we talk about sulfonation of benzene, we are more interested in the reaction that has to do with the addition of sulfur to a benzene structure. So when a mixture of benzene and fuming sulfuric acid is heated for about 8 hours, benzene sulfonic acid is formed. All right, so the compound where sulfur exists in here is what we call the sulfuric acid, which is H2SO4. The H2SO4 that is fuming, that produces fumes. So now this is the reaction. Now the reaction in the presence of, we say, fuming H2SO4. All right, now so we now have this. We now have this SO3H. Now this is called benzene sulfonic acid. Benzene sulfonic acid. All right, benzene sulfonic acid. Then the another thing you need to understand is that now this SO3 and HSO3 plus are electrophiles. They are electrophiles. Please take note of that. Okay, they are electrophiles. Now another one is halogenation of benzene. Another one is halogenation of benzene.